Hello, hello. Hi, everyone. Okay, so today we're going to go ahead and do 3.3 and 3.4. Funny enough, looking at these, I realize that they're just one page each, but I have a feeling that our homeworks are going to be pretty lengthy by the time you see this video, so don't see the timestamp and think, oh, okay, that's all I have to do. Okay, just giving you that fair warning. All right, let's start. So we're doing the mean value theorem. Remember the mean value theorems, or excuse me, remember previous theorem's idea was that if we have, a point here and a point here on a continuous function, then there exists some point in between where that function is at zero, right? So this has a similar sort of trick. Rolle's theorem, which we're going to talk about right now, is kind of an extension of the mean value theorem. So just keep that technicality in mind, okay? Let's start with Rolle's theorem. Rolle's theorem says let f be a continuous function over the interval a to b and differentiable over a to b such that f of a is equal to f of b. Then there exists at least one value c in between a and b such that f prime of c is equal to 0. For each function, verify that it satisfies the stated criteria in Rolle's theorem, and find all the values c in the given interval where f prime of c is equal to 0. Okay, so let's go ahead and see if we can even apply Rolle's theorem to this problem right here. So it says f has to be continuous, which I'm just going to write that's continuous on the side. Differentiable, it definitely is. We would just use the power rule for both of these guys. Let me write differentiable, check mark. And then it says that the ending intervals a and b, f of a and f of b are equal. So that we do actually have to check to see if this applies. So we're going to do f of -2, parentheses -2 squared plus 2 times -2. That's going to be a positive 4, and that's going to be a negative 4, so it adds up to 0. And then we have f of 0, which, I see what's going to happen here, but let's work it out anyway. 0 squared plus 2 times 0, well, we know there's going to be a glorified 0. So it's indeed that f of -2 equals f of 0, and that they match. Okay? Then there exists at least one c in between a and b such that f prime of c is equal to 0. Okay? Well, we need f prime first, and we know it's just 2x, and that's just plus 2. And then we're going to go ahead and not do it this way where we pick a c in between a and b. We're just going to solve for when this expression equals 0. So let's go ahead and solve for when this expression equals 0. So we have 2x plus 2 is equal to 0. And I'm going to solve for x, subtract the 2, divide by 2, and we have x is equal to -1. Now, it is indeed true that this c, where it's equal to 0, that -1, is in between our a and b, which in this case is in between our -2 and our 0. So the end, or let me write a little check mark here. So the ending result is that this satisfies Rolle's theorem, which we wouldn't have been able to figure out without all of this work. Next is B. So we need to do the same thing. It's the same prompt. Continuous. Yep, definitely continuous. Definitely differentiable. And then we just need to check for this bounded given that f of -2 and f of 2 equal. So let's do f of -2. -2 to the power of 3 minus 4 times -2. That's going to be -8, and this actually going to be +8. Okay, so we have another case where this equals 0. Then let's do f of 2. So we have 2 to the power of 3 minus 4 times 2. So this is going to be 8 minus 8, which is still 0, which still means that f of -2 is equal to f of 2. So they match. And like before, we could technically pick apart and be like, okay, well, let's try, negative 1.9, negative 1.8, and like look for it. But what we'd rather do is we know that we can definitely get an x value such that the f prime function equals 0. What we're really checking is we're checking if that value that we got is in between negative 2 and 2, or at least one of the values that we get, right? Because it just says at least one. So we may get multiple solution. We're going to get multiple solutions for this one for sure. But just keeping the verbiage intact when I say that. Okay, so f prime of x is equal to 3x squared minus 4. Okay, so let's put this equal to 0. And I'm going to add the 4. I'm going to divide by 3. I'm going to square root. So plus minus square root of 4 over 3. And this value is definitely in between 2 and negative 2. Well, values, right? Because it's a plus and a minus version. But I'm just going to quickly evaluate that on a calculator, although I'm pretty sure it is. Yeah, so the actual value approximate is plus minus 1.15. Yeah, I'll stop there. See? So, um, it's definitely both actually happen to be in between these two values. So, I guess I can write it like this. We'll say negative square root of 4 over 3, and then comma positive 4 over 3 is in between negative 2 to 2. And then again, this satisfies Rolle's theorem. Okay, next we have the mean value theorem. Rolle's theorem is a special case of the means value theorem. Let f be continuous over the interval a to b and differentiable over a to b. Then there exists at least one point C such that f prime of C is equal to this rate of change that we've seen before. At some point, the instantaneous rate of change equals the average rate of change. So if you're drawing between 2 points, the curvature, right? We know that technically speaking, that there is at one point, at least where they straighten out. So that's to add to this as well, is because you don't have to know like the context of why this exists. You just have to know it exists. I'm just giving you like the nerdish behind the scenes, I guess. We also have to recall that notice how this and this are eerily similar except for the verbiage stopping right over here and here respectively. This says that they're equal. Well, if they're equal and I plug them into this formula, you're going to get 0 over b minus a. And 0 divided by anything is still going to be 0. So that tells us that Rolle's theorem is just the special case when both of these guys equal. However, means value theorem is the more general, or not general, is the less general case. Okay? So let's start off, use the mean value theorem. Okay, so we're going to use it for A and B. Let's start with A. It says f of x is equal to the square root of x on the interval 1 to 9. So that means, well, first we do need to ask if it's continuous. It isn't continuous, but it is continuous on on 1 to 9. That is true. Because technically I've been kind of glossing over it. I'm just like, hey, it's continuous, who cares? But here it's continuous on that interval. So we can still use means value theorem. Then if it's differentiable, well, it definitely is. And then, or again, it's okay, it's technically not, right? Because if there was a negative value, that'd be an error, but it is differentiable on 1 comma 9. Okay, now if we construct this formula, we should get an appropriate value for C. So let's go and construct this expression first. Let's do f of a, or sorry, well, f of a, right? But f1, since it's the first entry, and we know it's just square root of 1, which is just 1. And f of 9, square root of 9, which is just 3. So we can get f prime of c to equal the following. So let's construct that first. We have f of b minus f of a over b minus a. I'm just rewriting it. We have 3 minus 1 on the top and 9 minus 1 on the bottom. That becomes 2 over 8, and that becomes 1 over 4. So it's a pretty random guess, right? That's kind of weird. Or I'm hoping you're making that connection. Like 1 over 4, why is that like, so we're saying that we can find a value where it's 1 over 4? Yes, it is an oddity, sure, but it's a valid application of the theorem. It lets us focus to where how these rates behave and their sort of interlocking connections that technically stack on top of other things to make more complex math ideas. So right now we're just learning like we're sort of scratching the surface for a harder math problem that we may get into. We may not, but we may get into. Uh, Give me a second. I'm recording. I'm so sorry. Huh? Okay. Right. Sorry. Okay. All right. Then we're gonna go ahead and for this, we need to solve for that c, but that c is f prime of x, which is just let's actually practice this out loud because I'm gonna be honest, I don't remember the square roots right away. But we can still just do it. First, we need to rewrite it as a power, and then we can go ahead and play with it as a power. That's going to be 1 over 2 x negative 1 over 2. And then we can go ahead and rewrite a bunch of this to be 2 square root of x. Okay. So that tells us that we can get this equal to this. Let's go ahead and just literally plug them in together. We have 1 over 2 square root of x is equal to 1 over 4. For this, I'm going to go ahead and cross multiply. Um, Let me go ahead and just highlight that. So if you don't remember cross multiply, it's that trick where if you have two fractions equaling each other, then you make an x, like I've done here, and multiply that line of the x, so 1 times 4, and then 1 times 2 square root of x, and then you copy the equals, and then you simplify, and ideally this is meant to help you solve for x a lot better, which it definitely is. So we do 4 2 square root of x divided by 2 to get 2 is equal to the square root of x. And then we can go ahead and solve for that, and we know that x is equal to positive or negative square root of 2. Okay? Now, the gimmick here, wait, let me double check that. Oh, I don't know why I did that. Excuse me. I am supposed to square the value, so it's 4. I don't know why I was square rooting a square root. That doesn't make sense. 4. So x is equal to 4. Okay? Now, we got a solution. And again, this is not relevant just yet because technically speaking, you can set, any polynomial, almost any function, especially at this level of mathematics, you can set it equal to something and you can go ahead and find an x where that's appropriate. The gimmick here, once again, is that there has to be the point in the interval such that this is what equals. So we need to double check if C is in between A and B. If our A and B is 1 and 9, and our C is 4, well, then we can definitely say that 4 is in between 1 and 9. And I've run out of space, but we can say that the mean value theorem works. Okay, now let's do B. So B says f of x is equal to sine of x on 0 to pi. Well, we know this is continuous for sure. and is differentiable for sure. So now we need to first set up that expression. So I'm going to do f of 0, f of pi. I get sine of 0, and that's going to be a 1. And I do sine of pi. That's not going to be 1. Hold on, real quick. Yeah, no, it's going to be a 0. And then that's also going to be a 0. Okay? So f of b minus f of a over b minus a is equal to 0 minus 0 over pi minus 0, which is all just going to be equal to 0. So let's go ahead and double check this. We're going to do f prime, and we see that's going to be cosine of x. So we need to solve for x when cosine of x is equal to 0. Well, technically speaking, right, this is a lot of things. This is x whenever it's equal to, you could say right away, pi over 2, but plus 2 pi k, and 3 pi over 2 plus 2 pi k. Recall your trig ideas where, you keep adding a 2 pi k in between all these guys, and you'll get a variable. Now, you could also, depending on where you learned this from, you could also just realize that these match together. Because of x is equal to 0, you know that this is doing every pi over 2, but you notice that this guy is doing 1, what's a good way to put it? I guess what's a good way to put it is listing it out. So if I were to list out this guy, I get pi over 2, and then I'm adding 2 pi. So I get 5 pi over 2. And then if I add another 2 pi, I'm going to get 9 pi over 2. If I subtract 2 pi, then I get negative 3 pi over 2. If I subtract another 2 pi, I get negative 7 pi over 2. That's for this guy. And then, for the guy right next to it, three pi over 2. I'm going to add 2 pi to that. So that's going to be 7 pi over 2. I'm going to add 2 pi to that. So that's going to be 11 pi over 2. I'm going to subtract 2 pi's now, just to show. I subtract 2 pi, I get negative pi over 2. Subtract 2 pi, I get negative 5 over 2, negative 5 pi over 2. And notice how all of these are just a pi away from each other. If I add pi to this, I get 3 pi over 2. If I add pi to this, I get 5 pi over 2. And so on and so forth. So that means technically you can combine this answer into a mega one. You can say that it's just pi over 2 plus pi k. Either way, though, because the gimmick with this is that does a solution exist in between 0 and pi? And it does, explicitly, when we have pi over 2, when k is 0, or over here in k is 0, and for this one doesn't work at all. We see that pi over 2, which is a valid solution, is in between 0 and pi. Thus, the mean value theorem works here as well. And we should box that because that's technically the resulting thing. But you do need all of this work, and notice how there's different ways to work this one out, but you need all of this work to verify that the theorem works. Same thing for Rolle's theorem as well. All right. The next thing we're going to learn is L'Hopital's rule. Now, when I was learning this, I couldn't help but call it the L hospital because I'm definitely afraid of reading. So I just was like, I'm not calling it that. I'm calling it L hospital. But it is called L'Hopital's rule. So just keep that in mind, especially if you're watching other videos of this. the person will say El L'Hopital, or maybe they'll make another joke like I did. But either way. All right. Let me go ahead and just start at the beginning. Limits at infinity. When evaluating limits of rational functions such as x is going to infinity, we compare degrees of numerator and denominator. So recall this idea. Okay. So for example, here, if we're evaluating that x goes to infinity, we see the degree of the top is greater than the degree of the bottom. So that's just going to go to infinity. And that's a top-heavy function. Because we have to pay attention. Oh, sorry, negative infinity. Because I was going to say we have to pay attention to the power, and we have to pay attention there's a negative in front of it. Okay? And then we jump to if it's balanced, if the leading coefficient of the top matches the leading coefficient of the bottom. So we see right here that these both have x squares. So that means this is balanced. You take leading coefficient of the top, divide by leading coefficient of the bottom, and you get that this limit goes towards -1 as x goes towards infinity. Over here, we see that the higher degrees on the bottom, so that's a bottom heavy function, so that means it'll go to 0. So let me write top, heavy, bottom, heavy, and balance. Okay. Before we move on, there's a couple of extra, hold on, I had it written down. There's a couple of extra ideas that I want to make sure that we are just technically aware of. Because recall the idea of a limit, right? It's as something goes to infinity, or something goes to that specific point, right? That it can go to infinity or negative infinity, depending. And when we include the evaluation of the limit at infinity, that kind of complicates things. So I'm going to go ahead and add some important limit ideas. First, we know that for a limit, as x goes to infinity, for a log function, such as ln, that's also going to go towards infinity. This is apparent from its graph. Similarly, for the exponential function, or any sort of base function that is a positive base, as x goes to infinity, this is also going to go towards infinity. Then reviewing some limits that we've talked about. Remember the idea of powers, right? So if it's an even or odd power, if it's a rational function too. So if the limit as x goes towards infinity for 1 over x to the power of n, right? The ideas with this, if n is, or okay, I accidentally wrote an easier one because I use positive infinity. Regardless of n, the gimmick here, or n being positive, that it should go towards infinity. The ones where it changes is x goes towards negative infinity. If I do 1 over x to the n, where n is even, then it'll be, it'll be infinity. But when, or not infinity, excuse me, the bottom will be infinity. The bottom will be infinity. And then when n is odd, the bottom will go towards a negative infinity. All of these vary, but in all these cases, we still have it to where that's going to be 0, 0, and both of these, even though it's even or odd, will also be 0. Okay? So just keep these sort of basic ideas in mind. We talked about all this before, and I did butcher it a little bit. I apologize. But this we definitely haven't fully talked about. It's the thing where we did talk about it in like the first couple section of limits where we're seeing how the trend line goes, and then you can make the association if you graph ln or if you graph the exponential function, you should see that as these go towards the right, they go towards infinity. Okay? This is important because these gloss over that idea where if you have the top part of a fraction and the bottom part of a fraction, if you have that one is going to infinity at a higher rate than the other, then that will determine if it's top heavy or bottom heavy. An easy way to decipher that previously, as of right now, was simply looking at denominators. However, in some cases with arbitrary functions like ln, exponential, we don't have that luxury anymore of seeing what reaches infinity at a faster rate. Bringing in a good instance of L'Hopital's rule. L'Hopital's rule is a tool for finding limits that are often difficult to evaluate. It can also help with determining limits at infinity. When evaluating limits by direct substitution, there are 7 expressions known as indeterminate forms. These expressions are 0 divided by 0, infinity divided by infinity, 0 times infinity, 1 to the power of infinity, 0 to 0, infinity minus infinity, and infinity to the power of 0. So all of these are the sort of annoying indeterminate forms that I believe I foreshadowed for you all in a previous video. But these are all indeterminate forms that tell us, okay, the limit needs more than just a substitution for us to evaluate it. L'Hopital's works explicitly with the 0 divided by 0 case or the infinity divided by infinity case. Let me read the rule. L'Hopital's rule. When direct substitution yields an indeterminate form of type 0 over 0 or infinity over infinity, then the limit of a quotient is equal to the limit of the top quotient's derivative divided by the bottom quotient's derivative. So we're taking the derivative of the top and the bottom in order to help us evaluate these limits a lot easier than how we did it for our Unit 1 material. So let's start over here. We have the limit as x goes to 5 for this guy. Well, if I were to plug in 5, I get 2, 5 squared minus 9 times 5 minus 5 over 5 minus 5. Well, I know the bottom I'm going to get 0 right away. The top is 50 minus 45 minus 5, which is 0 over 0. So thus, L'Hopital's rule, it has a valid application here. Let's go ahead and perform the derivative of the top with the derivative of the bottom and evaluate that. So let me just write it out just to visualize what we're doing. And evaluate those derivatives. That's going to be 4x minus 9 over 1. Or 1 plus 0 and then plus 0 here. Which is just 4x minus 9. So we're going to, again, try direct substitution for this. This actually doesn't have anything, breaking it. So it's just 4 times 5 minus 9, which is just 20 minus 9, which is just 11. So the limit here is 11. Now, granted, technically speaking, you could have done this the other way, but this is the fun, quick way to do it. Let's keep this going here. Again, we're going to evaluate the limit this time at -5. So square root of 4 minus a -5 minus a 3 over -5 plus 5. That's going to be square root of 9 minus 3 over 0. And we can see at the top part is going to be 0. So again, 0 over 0. Okay? So let's go ahead and instead evaluate the limit for this guy, but with the derivative on the top and derivative on the bottom. And then x plus 5. So the top is going to be 1/2 of, what is that? Let's write in parentheses. 4 minus x to the power of -1/2. And then times derivative inside was just a -1. And then that's going to be 0. The top is done. And the bottom is 0. Or the bottom is 1, not 0. So for here, we need to fix this up because this looks really messy. So I'm going to go ahead and rewrite that top part a little bit. Dividing by 1 means I don't have to worry about it as much. So I have 1 over 2. 1 over the square root of 4 minus x. And then multiplies by a -1. So I'm just going to put a -1 right here. Okay. Now I can use direct substitution to plug everything in. So I get negative 1 over 2 times 1 over the square root of 4 minus a negative 5. So negative 1 over 2 times 1 over the square root of 9, which is just 6. I mean, oh, I went too far ahead, which is just 1 over 3, which then the bottom becomes just 6. Yeah, sorry, I went a little too fast for that. All right, and that's our answer. Let's go over here. So limit as x goes to infinity for these two guys. Well, we see that both of these guys, the top part's going to be infinity and the bottom part's going to be infinity. So that's going to get really annoying. So what can we do? Well, let's use L'Hopital's rule. So limit of x going to infinity plays out for the top as 2x and for the bottom as e to the x, which unfortunately for us still means the same thing. But it means the same thing. So we can further insinuate that this limit, which is equal to this limit, must be equal to the another usage of L'Hopital's rule. So we have 2 over e to the x, which is just going to be 2 over an infinity, because infinity would be the higher thing. So we could classify this as bottom heavy. Although I haven't really used this notation much because it's a tiny bit informal, because infinity is a concept, it's not really a number, but it's a good strategy that if you want to start incorporating it, you can. I haven't been incorporating it yet, but you guys can. And then I'm going to be honest, looking at your test, I saw that some of you guys do incorporate that, which is good, but it's not necessary. You could just argue, you don't even have to write this. You could argue here that this will be bottom heavy because this will go towards infinity. And maybe you write something like that's what you write. E to the x limit goes to infinity. So I'll let you decide. But it's bottom heavy, which means that the limit is equal to 0. All right, over here, we have a technical issue where we have this huge expression. And with this huge expression, plugging in negative 2, we're going to get, I think we're going to get 0 over 0. Yeah, we're going to get 0 over 0 again. But I want to keep this example because it does point something valid. 8 times negative 2 square plus 20 times negative 2 plus 16. Okay, so the top part is negative 8 plus 4 plus 16 minus 12. And then over negative 8 plus, if that's going to be 8 times 4, and 8 times 4 is going to be 32, minus 40 plus 16. So that's going to be 40 and 48. So that's a 0. And then the top as well is going to be, what is that? That's going to be 20 and 20. So 0. So you could technically perform the derivative. Perform the derivative of the top and the bottom will lead you with 3x squared plus 2x minus 8, and then 3x squared plus 16x plus 20. And then I'm going to spoil it for you, but you are going to get through work that this is going to be 0 over 0. So what does that imply? That implies that you can do derivative again. And you'll get 6x plus 2 over 6x plus 16. And this is a bit harder to see, but it's not the end of the world here because you will get the value of, now that this no longer goes to 0 and this no longer goes to 0, now you can just do direct substitution. And you'll get 6 times negative 2 plus 2 over 6 times negative 2 plus 16. Negative 12 plus 2 over negative 12 plus 16. That becomes negative 10 over 4, which you can simplify to negative 5 over 2. And that would be your answer. Okay? Now, granted, I believe I did imply that this was going to be a balance function, but then I remembered, I'm like, oh, that's for x is equal to infinity. We're just taking x is equal to negative 2. But notice how derivatives, which at this point I hope has become a bit more easy, has made this a lot easier. Instead of figuring out how to factor this, maybe doing some polynomial division and solving it that way. Because technically that's what you should have done, right? If I given you this problem before unit 2 or this unit, right? You guys would have had to have factored all these and cancel out the common factors, which is a valid approach, but it's just, time consuming. This, although lengthy, is not really time consuming. It's just a lot of writing, which is not the same as time. Okay? All right. So just keep this in mind, guys. This video was a little shorter than usual, but it's because the homework is going to be pretty lengthy. So make sure you get on top of that as soon as possible. All right. I'll see you all in the worksheet video. Let me know if you have any questions. Bye-bye. Bye-bye.